So number 61, it gives you a function h of x negative x cubed minus x squared plus 5x minus 3. Okay, on this problem, we recognize we have a polynomial function, so we're asked to graph this. So the first step is to do what? Left and right hand behavior, right? So what is our left and right hand behavior for this polynomial function? Goes up on the left, down on the right. Now on your quiz I'm about to give you, I do expect for you to go through the steps, and I will put the steps on the board just for this quiz. You won't, on the test you're going to have a cheat sheet, so you can put your own steps, but for the quiz I'll put them up here. So what was the second step for graphing polynomial functions? X-intercepts. How do we find x-intercepts? Set the polynomial equal to 0, right? And then try and factor the polynomial. And this is where we have to come up with a method, you know, whatever method is best to do this. Okay? Y'all are going to have to redo your seating arrangements. Do you want to?
I'll sit back.
You want to sit somewhere else? Okay. So how would you go about factoring this? What's the standard steps for factoring?
GCF.
First, look for a GCF. Do you have greatest common factor here? No. Now, just FYI kind of question, could you factor a -1 out of this? Could you?
Yes.
Yes. Okay, but I'm not going to, but you could, right? All right. How many terms? 4, right? So I could try grouping, but grouping is not going to work. So that leaves me just with the synthetic division that we did last time. And to do synthetic division, we have to create a list of numbers. So our list is generated from looking at the number in front, which in this case is what? -1, right? The number in the back, which is -3. Now, -1 is the same as having a 1 out there, meaning that we don't have to come up with 2 lists. Whatever the list is for this one is the list we'll use. So what are the factors of 3? 1 and 3. 1 and 3, right? So positive -1, positive -3. I will look for that on your quiz. Now we go straight to the synthetic division. Inside the synthetic division box, I put -1, -1, 5, -3, right? And what number do I start with there? 1? Okay, let me start with 1 now. See if 1 works. Bring -1 down. -1, -2, -2, 3. That worked? Yes. So this tells me that I can break this down to be x minus 1, and then these 3 numbers give me what's left, right? And so it should be -x squared minus 2x plus 3. Questions? So where was the issue? I'm just curious who asked me this question.
It's just
Does another number work or no?
I just factored it from there because you can see what it is, but it was.
Okay, so whenever you get, this is kind of an important thing that I want to get across to everyone today, because we are going to move on to new material, but one thing that I really want to stress is that the whole goal of using this synthetic division is to try and get it to a quadratic. If you can get it to a quadratic, like this, then worst case scenario is you can use quadratic formula to figure out where the x-intercepts are. Now we can also keep doing synthetic division, right? Let me attempt synthetic division some more. My numbers are -1, -2, and 3. What number should I try?
1.
I should try 1 again, right? Because you're always supposed to repeat it. And does it work? I don't think it does. Oh, wait a minute. That worked again, didn't it? So that tells me that this becomes what? X minus 1. And then this one right here becomes what? Negative x plus 3. I mean, sorry, negative x minus 3. So here's where I'm at. The original polynomial function turns into the x minus 1 I pulled out in the very beginning, right, from the first synthetic division. The second synthetic division gave me those two. And then you get negative x minus 3. Right. Now I'm supposed to set that equal to 0. Do y'all see the double root there? X minus 1, x minus 1. So I could rewrite this as x minus 1 squared. I should put this here. Let's do this. Negative x minus 3. I need to see when that's equal to 0. So technically, what we're doing is we're setting each of these factors equal to 0 to figure out what our x-intercepts are. So I take this, x minus 1. I don't need to worry about the square. Because if I make this 0, it's 0 squared, it's still 0. So I set that to 0. I set my other factor equal to 0. And then solve these two equations. So add 1, I get x is 1. Over here, how would you solve for x here? You could add 3 to both sides, right? You could. It's not wrong to do that. And that would leave me with negative x equals 3, but that's not x, that's negative x. So divide both sides by negative 1 or multiply by negative 1. Either way, the signs on both sides change, and you get x is negative 3. Now, we're also supposed to determine the multiplicities to figure out bouncing and crossing. So the squared here gives me bounce, and then over here, because I have a 1 up here, I get what? Cross. And then we're going to go graph it. Now, the issue you may have run into, did you have an issue of where it was hard to see it was a double root?
I screwed up the
Factoring them?
I had negative x plus 1 when I factored.
That's not wrong. I'll show you
Yeah,
what happens. Yeah. Let me get back to it. Let me finish it off, and I want to show everyone one little thing there. Okay? So what's the next step after I find the x-intercepts, which I've done? Step 3, the y-intercept. To do that, you plug in 0 for x, and when I plug 0 in for x, I should have gotten negative 3. Right? And now the fourth step is to sketch it, right? So sketch. So how do we sketch? Start with what? The x-intercepts, which I only had negative 3 and positive 1. So if this is 0, negative 3, positive 1. Left and right hand behavior was what? Up, down? So am I supposed to bounce somewhere? Off 1, right? Okay, so I've got negative 3 coming up like that. I know I'm going to cross. I'm going to come up here. I'm going to bounce, and this will be my down, right? Like this. So now I draw it. I go like cross through negative 3. I come back up to 1, and I bounce through. Oh, what did I forget? Damn it. Y-intercept. Okay, here. Negative 3. Okay. Now, I did have some students asking me some questions about checking this in the back of the book. The book sometimes will add an additional point onto their graph that we don't do. And that's just because the book and the author does a slightly different approach. So I would not take off if you didn't have an additional point. All I'm asking for are x-intercepts, the y-intercept, and then where it bounces and crosses left, right hand behavior. That's all I want. Okay, now let me get back to kind of where some people may have got hung up a little bit. And this is really important to see this. We were at a point where we had x minus 1, and then it was negative x squared, was it minus 2x plus 3, right? Equals 0. Now, did you use AC method on this?
Yeah.
Okay, so when you did AC method, did you do negative 3, negative 2 like that?
positive 3.
Okay, because you have to have the fact that that's a 1 out here, -1. You have to go -1 times this, right?
Right.
Would give you -3, and then they must add up to be -2. So the numbers that would work would be -3 and +1. Okay? So then what you do is you're going to break this down. You're going to write the left end is -1x squared. You don't need the 1. The 3 on the end. Right? And then in the middle, we rewrite the -2x using these two numbers. -3x and +1x. And then what do I do with that in the middle there, or that thing in the parentheses? Grouping, right? Okay. So what can I pull out of the first two terms here? I pull out an x, right? I could also pull out a what? -x, right? Either way. So I'm going to pull an x out because that's what the first thing people said. I'm left with -x. What else is still in there? I'd still have -3, right? And then over here, to make this one match to a -x minus 3, I would need to pull what out? -1. And then out here we still have my x minus 1. And then what would this all in here turn into? Well, this right here. X minus 1 times -x minus 3, or the other way around, right? So you would get x minus 1 times x minus 1 times -x minus 3. Isn't that what we had? The other way? Isn't it? So now we're at the same point that we were at with synthetic division. Show you something. Not trying to confuse you, I'm just trying to show you that there's multiple paths to the same answer. When we were here, I said, what could you pull out of here? And someone said x, right? But someone else said -x, right? What if I would have pulled a -x out of here instead? -x would have been here, I would have had x plus 3 instead. Do you agree with that? Distribute this through, you get -x squared. Distribute this through, you get -3x. And then over here, what would I need in front of x plus 3? What would I have to have out here? +1, right? And now if you break that down using your grouping, you would get -x plus 1, that's this and this, and then the x plus 3, and that equals 0. Now is that what we had down here? Mm-hmm. Not exactly, right? It doesn't look exactly the same. And this is what I wanted to point out. This is the whole reason for me going back and looking at this. Is it obvious from this that I have a double root? X minus 1, x minus 1? Is that obvious there? Is it obvious here? Not as much, right? Because you might look at this and say, well, look, x minus 1 is different than -x plus 1. However, if I plug 1 in here, what happens? If I plug 1 in, I get 0. What if I plug 1 in right there? I get 0 also. In fact, if I take just this factor and I pull a -1 out of it, just this one, what would I have inside? X minus 1. So by pulling a negative out of this factor, you can see the x minus 1 twice. So it's a little tricky. It all just depends on what road you go down. Sometimes it'll be a little bit weird. Sometimes it's obvious. And there's not one right way and wrong way. It's just you got to be comfortable manipulating it no matter what. Hope that makes sense. Some sense. Okay, I'm going to do one more before our quiz, and I'm going to do 63 because that was requested before class by a student. So let's take a look at 63. We have p of x equals -x to the 4th. No, yeah, -x to the 4th plus 10x squared minus 9. All right, first step. What's our first step? Left, right behavior. What's my left, right behavior? It's what? Both of them down. Right? You have an even degree, you have a negative leading coefficient. So down, down. Do you think you're going to need the table? Remember I gave you that table? Think you'll need that for the quiz? Yes? What was it? Even, odd, positive, negative, up, up, down, 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 up, up, down. That's one way of looking. This is your leading coefficient. This is your degree. So we are looking at even, negative leading coefficient. So we're here. All right, what next? X-intercept. Set it to 0. And if you write out here x-intercepts, you know, it makes me happy because I know what you're actually doing. GCF? No. 3 terms. AC method? Well, it's not exactly x squared plus, right? Like it doesn't look like the normal quadratic. You could actually still use AC method on this one, but only because it looks a certain way. So let's forget that. Let's just go straight to the synthetic. So what's my list? 9. All the factors of 9. So 1, 3, and 9. And so I'm going to begin my synthetic. Now, we have to be a little careful here. We have to be real careful because we have a couple of gaps in here, don't we? The cube, there is no cubed up there. There is no x to the first power. So everywhere that they're missing, I have to accommodate for those with a 0, right? So what's it going to be? I'm going to have what? -1, 0, 10, 0, -9. Now what normally happens if you forget a 0? It's all wrong, right? I mean, so it's not one of those things where it's like, oh, you know, I forgot this. No, it's you forgot the 0, everything's going to be off after that. So be real careful, pay attention there. All right, let's try 1. -1 comes down, -1, -1. -1 comes down 9. 9 comes down 9 and 0. Oh yeah. Right? Now, I have noticed with some people that have also asked for some help is that what they're doing is they're just attacking this, just keep on attacking it with synthetic division, which is okay. But I always like to look at what you have. I mean, take just one extra line to rewrite what this is. Okay? What is it? X minus 1 comes from that, and then what's that? Negative x cubed, negative x squared, plus 9x plus 9, right? Now, when I look what's in the parentheses here, I say, can I factor that? Well, how many terms are there? 4. How do you try and factor 4-term things? Grouping? Will grouping work on that? It actually does. Watch. What can I factor out of the first 2 terms? X squared. Okay, I'll pull an x squared out. If I pull x squared out, what am I left with? Negative x minus 1. Now, in order for grouping to work, you have to have the exact same thing here, negative x minus 1. So how are you going to get a negative x minus 1 to turn into this? What do you have to multiply by out here? Negative 9. See that? And now this turns into x minus 1, and then what is all that junk here? X squared minus 9, and then negative x minus 1, right? See anything? Difference of squares, right? See this x squared minus 9? It's a difference of squares. So that can go down to become an x plus 3, x minus 3. So we have x minus 1, x plus 3, x minus 3, and then our last one is negative x minus 1. Now, could you have kept on doing synthetic? Yes, it would have worked. But just keep in mind that anytime, for me as an instructor, what I expect of my students is if it's cubic, if it's 4 terms, try grouping. If it's quadratic, try AC method. Do something like that, right? I mean, you can do it. It's not totally out of the realm of possibilities. Just try that. If that doesn't work, you can try your synthetic. So we do this. We set it to 0. Now, is this one here and this one here, are they the same? Remember on that other one, it was kind of hidden? If I pull a negative 1 out of here, what would I be left with? X plus 1, right? Is that the same as this? No. So those are different roots. So now I set each of those equal to 0. So I'm going to write out 4 different equations here. X minus 1, I need that to be 0. X plus 3, I need that to be 0. X minus 3, I need that to be 0. Negative x minus 1, I need that to be 0. Some of these we could have figured out just by looking. In fact, you might be able to just look at all of them. But that's 1. That's negative 3, subtracting 3 on both sides. That's positive 3, adding 3 to both sides. And this one, last time I asked how would you solve this, I was told move this over and then multiply both sides by negative 1, or divide by negative 1. How about just adding x to both sides? Could you do that? What would you get? So you don't have to divide by negative 1 if you do it that way. But you get the same result. So I have how many x-intercepts? 4. What do I do at each of those x-intercepts? Cross. So it's all cross, 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 cross. All because they were all raised to the first power, those factors. And so if we draw it, here's 0, here's 1, here's 3, here's negative 1, here's negative 3. I have zeros at each one of these. Wait, not at 0. Y-intercept, what is it? Negative 9. And then it was down, down, right? Down, down. And I should cross everywhere. So I cross, I come up, I got to go back down, come back up, come back up. Like a bird. Okay. You ready? Okay, please, let's clear your stuff off the desk. I want to see what you do on this. I want to see what you do on this. Not your neighbor. I know these seating arrangements aren't very great. Oh, take out a piece of paper, I'm sorry. Well, you can use these steps. I want to see what you can do with this information right here and me just talking about it right now. See how much of this stuff you can retain. Do you remember I was telling you about how, I think college algebra is a lot about just learning things, showing that you can do processes, right, steps. Imagine you're at a job and your employer just sat up there for almost half an hour telling you how to work a copying machine or something, right? And now they're just asking you, now you go make some copies. That's kind of the way I look at this. I've shown you how to do this. Now let's see if you can retain that and produce, all right? All right, so before you get started, let me just kind of write these on the board. all right? The first one, f of x, is x to the fourth plus x cubed minus 12x squared minus 28x minus 16, right? But check this out. I'm going to tell you right now that that's actually x plus 2 squared times x minus 4 times x plus 1. I want you to graph this, but what have I already done for you? I've already factored it, okay? So this is really just, can you follow those steps? And the main, most difficult step, number 2, has already been done for you, okay? So I want to see whether or not you can, I want to see whether or not the factoring part is the part that you're getting hung up on, or if it's just the whole thing you don't know what to do. You know what I'm saying? Now, number 2, you do have to do the work. So number 2, if I promised you just one problem, I apologize. On number 2, you do have to go through the steps, okay? There you go. So for both of these, give me a sketch. Follow the 4-step process. I'll give you one hint. Grouping will not work here. All right?
So number 1, you don't have to factor it, you just put x.
When you say x-intercepts, right, you set the function to 0, and you try and factor, well, it's already factored. Something that I could do on a test instead of this is just add an x squared to all of these. So make it something like this, where it'd be like x to the 5th minus 8x to the 4th plus 5x cubed plus 14x squared. So everyone see all I did was just multiplied everything by x to the 4th? And so when you go through this, your first step, it would go down on the left, up on the right. The second step, you set it equal to 0, right? And you would factor an x squared out first. And then you would do this right here with your synthetic, right? And you'd still have the x squared out here. Is that all right? Now, what were the factors? Does anyone remember what they were? Let's see. How about, oh, I know what they were. Minus 2 plus 1 minus 7. Those were the 3 factors that you should have gotten. And then you would go through and you get your y-intercept. What's your y-intercept here with this one? Careful. Careful. If you plug 0 in for x, what do you get? You get 0, right? See, it's not the number by itself because there's an x there. So it would be 0, 0, 0. So you just get 0. Y'all see that? Okay, so let's put everything together now. I have my x-intercepts, which are these, right? I have to get them from here. What about this one? When is that 0? Well, let's do this one. How about that one? When's that 0? When x is 2, right? When's this one 0? Negative 1. When's this one 0? 7, right? This would be cross, 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 because the 1, 1, 1. But what about this one? 0. When is x 0? When x is 0. But what would you do at 0? You'd balance because you have a square. See the difference between this problem and the one before? The one I gave you on the quiz? So your picture is going to look different too. You would have, let's see, an x-intercept at 0. You would have one at 2. You would have one at 7. You would have one at negative 1. Your y-intercept is also 0, isn't it? Which, doesn't that make sense? Because that's right there at the origin, that's 0. And then you are going, what was it, down, up? Down, up. You'll cross everywhere except 0, you'll bounce. So it'll be like cross, bounce, cross, cross. Y'all look thrilled.
Cross or a bounce?
What's that?
The 2. Looking at what you said.
Cross is here, because the power on the factor is 1. If the power on factor, right? And remember, it's not the number. It's not if the number's odd or even. It's if the power on the factor is odd or even.
So even if the y-intercept is 14, you still...
The y-intercept is not 14, though.
Oh, it isn't?
No, because remember, to get y-intercept, right? To find y-intercept, what do? We figure out what f of 0 is. That means we plug 0 into the function. Now, the way I had written it, right, it was x to the 5th, blah, blah, blah. The last term we had was, what, 14x squared?
Yeah.
If I put 0 in here, it's going to zero it out. Now, in the one on the quiz, there was no x here. So your y-intercept would have been 14, right? This is not what the quiz should have been. This is what my modified problem of the quiz would have been. The quiz would have looked like this. What was it, -1, 2, 7, and then we would have had 14 up here. It still went down up, right? But it crossed everywhere. So we would have done that.
We need to write cross, bounce, cross, or whatever, here between just
Just write it. I'm not even asking you to write crossbound. I'm just writing CB. You know what I'm saying? Just so I can see down there, like that's where you identified it, as opposed to you completely forget to do that. You know what I'm saying? And you're just going off of what you think looks right. If you do that and it's wrong, I'd like to see that you were thinking bounce cross. You know what I'm saying? All right, well, that's going to do it for 3.4. Remember that we don't have class on Thursday, right? Yes? Pardon? What did I what? Oh, it's almost 3. Okay, sorry. I don't know if this is going to work real well. We'll give it a shot. Yeah, no, the soccer game, that's, yeah, it's apparently a big deal. No, I'm going to lecture, but I'm going to just put it up there with no volume, so you can kind of keep track of things. I got popcorn. So let's kill one of the lights. How about, would you mind, Robin? The one that's, I think they're in the order of the room, so let's see. Yeah. Now I can't make it any bigger because if I do, it gets real choppy and then it stops and pauses and I have to go over there and move the mouse. So it's as good as we're going to get, okay? All right, so try. If I feel like everyone's watching the game and not me, I'll turn it off, okay? Oh wait, I don't want the volume on. That's all right. So now we're going to move to 3.5. In my experience with teaching this course, these are the most difficult functions to graph because there's a lot going on when you start talking about rational functions. Polynomial functions came down to 4 steps, right? Left, right-hand behavior, that was pretty easy, right? Left, right-hand behavior. And then the zeros, now that was different. The x-intercepts, that took some work. But after that, it was pretty much just put it all together, bounce across, we were done. These functions do not behave as well. So we have to do a lot of work to get the pictures. So first of all, what is a rational function? Well, a rational function is any function that looks like this. It's a polynomial divided by another polynomial. I'm just going to put poly over poly. Now, what are polynomials? That's what we just studied, right? So take one of the things that we just graphed and divide it by another one. And now you have what's called a rational function. So you can imagine that they're going to look pretty nasty. Now what we will say is we will call this top one n of x and we'll call the bottom one d of x. Why do you think I called it n of x? Numerator. So this is our numerator polynomial, and then d of x for denominator. That's our denominator polynomial, right? Now we do have some things we have to be careful with. Our denominator can't be 0, right? Because what happens if our denominator function is 0? It's undefined, right? And so we have to stay within the realm of math, right? We can't divide by 0. All right, so I think one of the best ways to kind of get a feel for what's happening and how these look is to just take a specific example and draw it, and then start to look at some of its characteristics. And then after that, we'll start labeling things and defining things and giving us a formal, I'll give you like a formal set of steps. So let's start with this one. Let's make that x plus 4 over x minus 2. Okay? So, do you agree that the numerator is a polynomial? It's a line, isn't it? X plus 4 is a line, but lines are polynomials. We said that already. The denominator, x minus 2, is another line. So we do have a polynomial divided by a polynomial. So if we're going to try and graph this, let's go back to the first way we ever learned how to graph anything, and that was using this thing called a t-table. Remember the t-table? You plug in a value of x, and then it spits out a value. Right? So we just tried plugging them in, and we just got a bunch of points and then drew them. So let's just plug a value in for x. How about 0? What happens if I plug 0 in for x? What do I get? I get 4 on top and on the bottom. -2, what's 4 divided by -2? -2. So I could start a graph now. Let me try and start my graph over here. I know that when I plug in 0 for x, I should be at -2. So this is like a point, right? I'm talking about the point 0, -2. So that means I don't move left or right, but I go down 2. And I should have a point that lives on my graph like that. Let's try another point. How about 1? Let's plug in 1. What happens if we plug in 1? We get 5 on top, right? And then what do we get on the bottom? -1, so you get -5. So now at 1, to the right, I go down 1, 2, 3, 4, 5, right? Do you all agree? Okay, and then I can keep going, right? Let's try 2. You're squinting. Can you not see, or you have a question? You're okay? Okay, so if we plug in 2, what happens? On top we get 6, and on the bottom we get 0. Uh-oh. What happens when you try and divide by 0? It's undefined. Undefined. It's the other way 0, right? So that's undefined. That means my graph cannot exist here. It means if I go to 2 and try and plug it in, there is no graph. Remember we talked about domains of functions? 2 is not in the domain. So what's going to happen here? Well, I'm not quite sure yet, all right? So let's just move again. Let's go to the next number. How about 3? Let's plug 3 in. If we plug in 3, what do we get? On top we get 7. On the bottom we get 1. And 7 over 1 is 7. So now look at this. Weren't we down here? And now at 2 it was undefined. Then at 3 we're up here at 7. Right? Okay. So we were negative value here, we were negative value here, and then 2 was all jacked up, and then we got to 3, where all of a sudden we're up here, right? All right, let's try something else. How about...
Why are you not on the line?
Why am I not on what line? This? I'm plugging these in as points, like ordered pairs, like an x and a y coordinate. This is the x coordinate, this is the y coordinate, right? Input, output. So this one right here, I go to the right 1, down 5.
Okay.
3, 7. Okay? What else? Should I try something else? How about 4? We'll just keep going. 4? What happens when I plug in 4? On top 8, on the bottom 2. 8 over 2 is 4. So now at 4, instead of being up here at 7, I'm down here at 4 now, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. So I'm here. What about 5? Where am I? 9 over 3, which is 3, right? So now I'm here. So what looks like is happening now as I go to the right? Looks like it's getting smaller, right? Okay. Let's go maybe one more. What happens at 6? 10 over 4. 10 over 4 is same as 5 over 2, right? What's that? 2.5? So now I'm at 1, 2.5. I'm right here. So it still looks like it's coming down. Sorry, I need to silence my phone here. Right? What's going to happen as I keep coming this way? What do you think is going to happen as I move to the right?
Closer.
Closer to the x-axis, you think? Kind of. It is going to get closer to something, but it's not going to be the x-axis. And you'll see why. Let's go crazy. Let's just go way out there. Way out there is kind of subjective, isn't it? Let's go to 10. What would we get if we plug in 10? 14 over 8. What's 14 divided by 8? Well, that's the same as 7 over 4. So if you get on your calculator and do 7 over 4, you get 1.75. Is that right? 1.75. So if I'm way out here at 10, I'm only at 1.75. So 1.75 is about right here. And I'm eyeballing ballpark this now. Okay, just that seem okay to you? I'm out here. I'm going off my video. Well, let's go even like further out. Let's go to like 1,000. Okay, let's go to 1,000. See what happens. So plug 1,000 in and tell me what you would get. Now you might need your calculator. What's the top? 1,004. What's the bottom? 998. Get your calculator and do 1,004 divided by 998. Tell me what you get.
1.106.
1.006? Like that?
Oh, it's 4, and it's like additional numbers, but
Oh, does it?
yeah, there's more numbers. Yeah.
Is that okay? Yeah, there's more numbers, but that good enough? That's really close to 1, isn't it? Let's go even further out. Go 10,000 out. Wouldn't that be 10,004 over 9,998? And if you divide, what do you get? 1.000. So whatever it is. It's getting really, really close to what? 1. Okay? So yes, I agree, it is dropping down, but there's this flat line that it never gets below. And that flat line, I'm going to represent it right now with a dotted line. See, I'm 1 unit up, right? 1 right here. If I take that 1 and I draw that horizontally all the way across, then it looks like my graph is getting closer and closer to that dotted line. Do you agree?
Yeah.
Okay. Now, we still don't know what was happening at 2. Did they score anything yet? At 2, we still said that was undefined. Let's go this way now. Okay? Let's go the other way. Negative. So let's try some negative numbers. How about -1? Look, this is not the way we're going to graph rational functions. All right. This is just to get us to see what they look like, and see it locked up on me. -1. What happens when I plug in -1? 3 on top, -3 on the bottom, so we get -1. So at -1, I'm here. Now remember where I was. At 0, I was right here. Now I'm right here, right? Let's keep going that way. What happens at -2? The top becomes negative 2 plus 4, right, is 2 over negative 2 minus 2 is negative 4. So doesn't this become negative 1/2? So at negative 2, I'm here. So what does it appear is happening here? Coming up like this, right? So where does it look like it might head? Well, how can you tell? Just keep going, right? So let's go crazy again. Let's go way out there. How about negative 10? What would you get if you put negative 10 up there? Oh, you know what? Hold on. I want to put negative 4 in there. I need to get to negative 4. Let's put negative 4 before we do negative 10. What do you get if you plug in negative 4? On the top, you get what? 0. On the bottom, you get negative 6, don't you? 0 over anything is 0. So at negative 4, I'm at 0. What is that point called where we hit this axis? It's called the x-intercept, right? Here we actually had a y-intercept, didn't we? Okay. Now let's go further out. How about negative 100? What happens if you plug in negative 100? We get negative 96 on top, right? And then negative 102 on the bottom. Someone do that for me.
0.94.
0.94, approximately 0.94. That's almost 1, isn't it? Now let's go even further. Let's go negative 1,000. That'd be negative 9,000. 996 over negative 1,002. 0.99. And the further you go out, the closer it gets to 1. All right? So what we have is that same blue line that we had, right? Is the same thing we're going towards over here. So our graph looks like it's getting closer and closer to that line. Agreed? So I'm going to start drawing this thing, all right, because we have a lot of the picture. We still have to come back and talk about what's happening at 2. So this graph does something like this, okay? And then over here, it does something like this, right? Right now, just looking at that, does that look like a polynomial? Polynomials is what we just studied. No, polynomials have to be smooth and curved, right? This is smooth and curved, but look, it's flattening out, isn't it? It's flattening out. Remember, we had left, right-hand behavior on the other ones? Up, down was the only option. Here, it's flattening. That's already different than what we've seen. Oh yeah, I forgot this point down here. I have to get down to there. Can y'all kind of tell what's happening at 2? Just look at the graph. Imagine that you're on this roller coaster and you're moving towards 2. What looks like is happening?
2 has a force field.
Yeah, it's almost like a force field, right? It's like you cannot go there. You've got to turn up away from it, right? Or if you're coming in this way, same thing, right? It's like you're headed towards 2 and the function's like, oh shit, what do I do? Oh, and it's just like taking off down. That's pretty much what's happening, right? So what we do is at 2, I want you to draw a vertical dotted line. And now let's just verify that something crazy is happening towards 2. So let's pick something that would get us pretty close to 2 over here. Like, let's try 2.001. Do you agree that's really close to 2? Yes? I would like to plug 2.001 into the function and see what happens. So I need my calculator, people, to take 2.001, plug it in up here, and we get, what, 2.001 plus 4 is 6.001 divided by 2.001 minus 2 is 0.001. If you do that on your calculator, what do you get? 6,001, right? That means if I try and draw the point that's right here, I go out 2.001, I need to go up where? To 6,000. So that verifies that what's happening here is my function is taking off up forever. But what's happening at 2? At 2 exactly. It's undefined. The function does not exist there. If you move anywhere outside of 2 on this side, you're going to be way up there somewhere. And as you move across, it starts to get smaller and smaller until you get to 1. Right? It gets closer and closer to 1. Does it ever touch 1 here? No, it never gets to it. All right? Now, we could plug in a point on the other side, like over here. What would be a good number to plug in on the other side of 2, on this side? 1.99999 or something like that? Now, we won't go through it. But if you plug 1.999 into the function, you're going to get a huge negative number. And so that will verify that what this is doing is it's diving down forever like this. Okay? That is our first complete drawing of a rational function. Most rational functions have certain characteristics that are on this graph, so that's why I always start with it as an example. So let me label the things that are important on this graph. Okay? First of all, things that we've already seen, we call this point right here an x-intercept, right? X-intercept would be anywhere that our graph exists on the x-axis, right? Anywhere that our graph exists on the x-axis would be an x-intercept. The point right here, let me get these out of here. This point right here is called the what? Y-intercept, right? That would be anywhere that our graph touches the y-axis. Then what we have are these dotted lines, right? These dotted lines. This one is a horizontal line. This one is a vertical line, right? This vertical line is called a vertical how do you say that? Asymptote. It's one of those weird words that isn't quite spelled the way it's pronounced, or it's just a weird spelling. So you just try and say it real fast so people can't tell whether or not you're getting it right or wrong. You know, you say vertical asymptote, real quick. Vertical asymptote is a vertical line that behaves like a force field, like a barrier, okay? So I'll talk about it a little more later. I'm going to say what a vertical asymptote is, how we find them, etc., right? Then this horizontal one is called horizontal asymptote. Okay. Now, you do not have to have a vertical asymptote on a rational function. It does not have to have one. All right? And it does not have to have a horizontal asymptote. It does not have to have an x-intercept. And it may not even have a y-intercept. But if it does have vertical asymptote, this is the way vertical asymptotes behave. They force your function down or up. Horizontal asymptotes, how could you describe to me what a horizontal asymptote is doing to your function? Pulls left, right, never touches it. Well, it's all going to depend on how it makes sense to you in your mind. The thing that most of my students in the past have always liked is that this horizontal line acts like a magnet, and it pulls the graph towards it as you go out to the right. So as you're drawing it to the right, you're getting pulled towards this dotted line, right? As I go out to the left, I'm getting pulled towards this dotted line. Where the vertical asymptotes force you up or down. All right, before I erase it, I want to see if you can make a connection here. What is the equation of this vertical line? Can anyone give me the equation of that vertical line? Remember lines? Lines all look like y equals mx plus b, but if it's a vertical line, we write it x equals 2, right? So this is the vertical line, x equals 2. What happens when x is 2? It was undefined down here, right? So it might be that we will have vertical asymptotes whenever we have our denominator 0, right? If x is 2, it creates this, what we call, oh my gosh, that's how long I've been out of school. a pole. Sorry. Ooh, man. We call these poles because it's like our function blows up at the pole. Okay, there's this pole right here, and the function as it approaches it goes up forever. All right. So if x is 2, we have this vertical asymptote. Now, what about this x-intercept? What is this x? What's the value of x here? The value of x. -4. Can you tell what that comes from that picture? From the function? If I let x be -4, what do I get up there? 0 on top, right? So look, what I'm trying to get you to see is that the vertical asymptote happens when the bottom is 0, right? The x-intercept happens when the top is 0. What about the y-intercept? When does that happen? Well, how do we always get y-intercepts? Let x be 0. If x is 0, what do we get? 4 over -2, which is -2. So 3 things now. Vertical asymptote occurs when the bottom is 0. X-intercept occurs when top is 0. Y-intercept happens when x is 0. And the last thing to figure out is where this comes from. And that's a little harder to do. All right? Figure out why this thing wanted to go to approach 1 on each side. So we'll leave that to, that's where we're kind of headed here. Okay, it's been an hour, 15 minutes. Y'all want to take a quick break, and we'll come back and put it all together? Yeah? Okay. All right, we're going to be able to do this, you think? I'm just going to wait for that to cut out. When it cuts out, I'm not going to start it again. So let me list out the characteristics of rational functions, the things that we look for. First of all, x-intercepts. Okay. So for the x-intercepts, does anyone remember where that x-intercept came from on that example? It was when the top was 0, right? So to find the x-intercepts of a rational function, what we're going to do is set the numerator equal to 0 and solve. Right? That's how we will find our x-intercepts. We will set the numerator equal to 0, we'll solve that equation, and we'll plot those, right? These are going to be points on the x-axis. Okay, that's x-intercepts. The next thing that we're going to look for are the vertical asymptotes. Now, instead of writing vertical asymptote over and over and over, I'm just going to say VA from now on. Okay, is that all right with everyone? The vertical asymptotes? Where did the vertical asymptotes come from? When the bottom was 0, right? When it was undefined, so when we had division by 0. So to find them, what we're going to do is we're going to set the denominator equal to 0 and solve. But it's important for us to understand what it is these are, right? The x-intercepts were point on our x-axis. What are these? What were those vertical asymptotes? They're like these barrier things, right? That's what we were talking about. So I'm gonna kind of describe them here. These are vertical dotted lines. Are they technically part of your graph? I mean, are they, like when we drew the polynomial, it was like a roller coaster up and down? Are the dotted lines part of, are the dotted vertical lines part of the graph or not?
No.
No. I only put them there to kind of help us see where it was happening, but the dotted lines is technically not part of the graph. So keep in mind, we will draw them, but they are not part of the graph. Make sense? So vertical dotted lines, and we can't cross these. You can never cross a vertical asymptote, and it forces the function up or down? Remember on that drawing that I just had, when we came in on one side, it went up, but when we came in the other side, it went down. So we'll have to figure out up or down. We'll have a way of doing that later. Okay, so that's what we'll do to get the vertical asymptotes. We also had y-intercepts, right? Y-intercepts. So how do we find the y-intercept? It's the same we've been doing since the beginning. We take 0 and we plug it into the function, right? Plug 0 into the function, whatever it spits out, that's our y-intercept. Where does the y-intercept go? I mean, like, what is it in our drawing? It's a point, right? It's a point. Y-intercept is a point, but it's on the y-axis. Barely see that. Right, so we have x-intercept, that's points on the x-axis. We have vertical asymptotes, vertical dotted lines. They're barriers, they force us up and down. We have the y-intercept, a point on our y-axis. And then the thing I say for the very last is the horizontal asymptote. So the horizontal asymptote. Let me tell you how you find these, and it's not as simple as we would hope, all right? What you do is this. You compare the degree of the numerator to degree of denominator. When I say degree, what am I talking about? The power, the highest power that you see, right? So what you're going to do is you're going to look at the degree of the top, and then you're going to look at the degree of the bottom. And you're going to compare those two numbers. When you have two numbers and you compare them, what are the three possibilities if you compare two numbers together? What are the three things that you could have? So let's say I have a number, n, which will be the degree of the numerator, and a number d. What are the three cases I could have? N could be bigger than d, right? The numerator's degree could be bigger than the denominator. Or you could have the numerator's degree is less than the denominator, right? Or you could have what? They're the same. This in mathematics is called trichotomy. The only three possibilities when it comes to numbers, the relationship between them is one of those three things. All right. So next to each of these, I'm going to tell you what you do. Okay? If the degree of the numerator is bigger than the denominator, then we have no horizontal asymptotes. You don't have any. So you don't have a horizontal dotted line that your function goes down towards. You don't have it. If the numerator degree is less than denominator, then y equals 0 is your horizontal asymptote. What's y equals 0? X-axis. It's y equals 0. Y is up and down, right? If y is 0, then we're talking about the x-axis. So that means the x-axis will be your horizontal asymptote. And then what if they're the same degrees? Well, this is the trickiest case. And I'm gonna put it up here because I'm getting kind of low on the board there. If the numerator and denominator's degrees are the same, then you will have one, and it will be this. Y equals not 0, not 1, not 2. It'll be exactly this. It'll be the leading coefficient of the numerator divided by the leading coefficient of the denominator. And I'm going to go through and explain how that works. Now, help me out here. Let's describe what these are. Because if I have one, I want to be able to draw it on my graph, right? What is it on my graph? Horizontal, right? Dotted. line, horizontal dotted line. And now I'm going to put something here I did not do when I first exposed you to the rational function today. I'm going to put drawn at ends only. So if you go back and look at the example I did a second ago, my horizontal line went all the way across my graph, right? Didn't it? All the way across. It's actually, I only want us to draw it at the ends from now on. And you'll see why as we move on. So that's what it looks like. It's a horizontal dotted line drawn only at the ends. But what is the characteristic of that line? I told you that, what does it do to your function?
It attracts it.
Attracts it. Okay, so it pulls your function towards it, right? We'll say that. It pulls or attracts your function to it. And then again, ends only. So those are the main characteristics of rational functions. X-intercepts, vertical asymptotes, y-intercepts, horizontal asymptotes. If we can draw all those things, get all that information on a piece of paper, we should be able to draw the function. Well, we should get real close to it. All right, here we go. You ready for us to try? To draw one? They'll look thrilled. Now, I know this may seem kind of dumb, but let's just do the one we just did, okay? But let's do it without the t-table. Yes? Sorry, it was a coin. All right, so I have not given you the formal steps yet, okay? Because I want you to see that as good as what we've got right now, there's still one thing we're going to need to address. Let's start with the x-intercepts, all right? Start with the x-intercepts. How is it that I said to find the x-intercepts? Set numerator to 0. So my numerator is x plus 4. I'm going to set x plus 4 to 0. I solved that equation. Can you solve that equation? Move the 4 over. X is negative 4. I'm going to box that up. That is a point on the x-axis, isn't it? A point on the x-axis. All right. The next thing I'm going to do is find my vertical asymptotes. I may have 1. I may have none. I may have 5. It just depends. To do this, though, I set the denominator to 0. So my denominator is x minus 2. Set it to 0. Solve that, add 2 to both sides. Questions on that? Next step, or the next thing I said we can find is the y-intercept. How do we find the y-intercept? Plug 0 into the function. What do we have? 4 over negative 2, that was negative 2, wasn't it? Do we have any questions up to this point? The horizontal asymptotes. Okay, this was the one that was tricky. What is this is where we compare the degrees, right? What is the degree of the numerator? 1. Right? The degree is 1. The highest power of x is 1. What is the degree of the denominator? 1. So wouldn't you say here that the degree of the numerator, which let's call the degree of the numerator, let's call that n, let's call the degree of the denominator d. Do you agree that in this case n is equal to d? Right? They're equal? What do you do when they're equal? Well, I said you'll have a horizontal asymptote and it'll be y equals what? Leading coefficient of the numerator divided by the leading coefficient of the denominator. So now I have to go back up to these and I have to look at their leading coefficients. What's the leading coefficient of the numerator? 1. You're looking at the number in front of x now, aren't you? You're not looking at the power. You're looking at the number in front of it. So if that would have been a 2x, you would still have had the same degree, but that you would have a 2 instead of a 1 in front. So I put 1 up here, then divided by the leading coefficient of the denominator, which in this case is what? Also 1. And therefore you get 1 over 1, and 1 over 1 is 1, and that explains where that 1 came from. Okay? Now, let's see if these 4 pieces of information are enough for us to draw a graph. Okay? Let's see if it's enough. I claim it's not. We just need a little bit more. All right, everyone have that information down? Get rid of it? All right. Okay, here we go. Start by drawing x and y axes. Now let's start with the first thing we found. First thing we found was an x-intercept, right? And it was -4. So that means x-intercept -4 means I go to my x-axis, I go to -4, I draw a dot, right? 1, 2, 3, 4, -4, I draw a dot. What was the next thing we found? Vertical. Where was that? At x equals 2, right? Now, when you do this, let me show you what people do that's a mistake. They'll do this. And then they'll draw a dotted line. They say, oh, wait, it's a vertical asymptote. I need to draw a dotted vertical line, right? I warn you to not put a dot, okay? It's a vertical dotted line, right? Your graph doesn't go through there. It's a place that your graph actually can't be. So make sure that you know what you're graphing. The vertical asymptote, vertical dotted line, draw the dotted line, you're done. Next thing. Y-intercept was what? -2. Next thing. Horizontal asymptote, 1. I should have stressed a little more. Y-intercept -2. Is everyone okay with the fact that y-intercepts are points on the y-axis? Okay, so the horizontal being 1 meant that y equals 1 means I come up to 1, right? I draw a horizontal dotted line, but what did I tell you? Only at the ends, right? What I mean by that is move out to the right quite a bit, like about right here, and draw a dotted. And then over here, get past all your information. Like I have a y-intercept, I have an x-intercept, get past that, and then draw a dotted line there. Okay? You all right with that? Is that enough information to draw the graph? Well, let's see. If I'm at this point right here, let's think through this logically, all right? If I'm at this point right here, and I try and draw my function out to the left, and I have a dotted blue line up here, then don't I have to go up to it? I mean, isn't that the whole idea of the horizontal asymptote, is that it pulls your function toward it as you go out that way? So would you agree that I have to go like that here? Could I do this and then come back up and do it? Why not? It's not what? I mean, that still goes towards that line to the left.
But should it be continuously going?
Perhaps it could be. But I did something else there. I crossed the x-axis again, didn't I? Look, I came down and then I came back up, and didn't I cross the x-axis? Well, that means I should have had an x-intercept there, right? And I don't have an x-intercept. That's the only x-intercept I have. So it's impossible for me to go down and then come back up like that. I can't do it, right? So I have to, once I start going this way, I have to stay up that way. So it is okay for us to just draw to the left like that. Look, the only place that I'm ever going to pick up my pencil or pen is when I get to that vertical barrier, right? That's the only place. Everywhere else I should be able to draw it without picking up my pencil. So it's like connect the dots from grade school or like elementary pre-K. I'm trying to connect the dots right now. If I move to the right now, where do I have to go? To this dot right here, right? I have to go there. Now, could I have bounced off and then gone down to that dot? Why not? Because I'd be crossing the x-axis again, right? And you're not allowed to cross anywhere except here, possibly. So that's not possible. See, look, it becomes at this point a process of elimination, and you have to think through it. I have to go from here to here. I can't go up. So I'm going to go ahead and connect these together like this. And now, from this point, what happens? What's that? Pulls and it goes down? Why not up? I mean, the vertical barrier forces, I know it forces me to either go up or down. I'm never sure which one it is. But you're right, it is down, but why is it not up? I mean, why can't I just say, you know, you hit the brakes and then cut up like that? Because I'll cross the x-axis again, right? So I cannot turn back up. Can I do this? Can I go like this? Like, screw that, I'm going to just take off that way. Why not? Because I crossed the y-axis, but even more important than that, what did I do? Let me do this. Could I have done this? Could I have gone and gone? Whoa, forget that, man. I've turned back on myself, haven't I? Vertical line test. Is this a function anymore? No. See, this has to still be a function. So you can never turn back on yourself like that. That'll be one test that you need to do at the end of your exam, that when you do problems like this, when you're looking at your final picture going, there it is, you want to do a vertical line test real quick and make sure it looks like a function. Okay, so by a process of elimination, this thing must go down. Now I get to my vertical, I have to pick up my pencil, and I have to come over here and make sense out of this. Can you determine, without any other information, what's going on over there? What's that? Can it mirror that? What does this tell you? Your graph has to head towards that, right? As I start drawing out that way, which, by the way, we call infinity, as we go out to infinity, my function is trying to get closer to that line. As I come to the right, this barrier is going to force me up or down, right? Can it be up or down, or can it only be up or only down? I mean, can you tell me? From just this, can you tell me? Can it do this? Is that okay? Yes? Can it do this? I'm trying to get you all to think through this. Do you agree that this blue line tells me I eventually have to be either getting close to it like this or like this? Like, I have to be approaching that, right? So do you agree I have to be up there somewhere?
Yes.
Okay, now if I'm up here somewhere, can I get down there and go down forever? Why not? I just crossed the x-axis, right? To get from up here to down there, I have to cross the x-axis. So that's not allowed, because I don't have an x-intercept there, right? So to be here and then to go this way and hit the vertical is going to have to force me upward. So I can just put that all together right now and draw it. Again, process of elimination. I don't know how to teach that. I just show it, and hopefully you start to pick up on the ideas. All right. Now that's our picture. That's it. We're done. We're finished with this problem. Now I would like to talk briefly about where these functions come into play. When we first started talking about functions, we talked about lines. Do you remember that example we had of like so-and-so, well, the exam problem was like so-and-so sells cars and they make so much per day and then however many cars, and that was a linear graph, looked like a line. And then we talked about parabolas. The parabola looked like this, and we could use that to describe, right, vertex, axis of symmetry, x-intercepts, all that stuff. We talked about these, and that was good for like modeling objects that are, you know, thrown through the air. It's good for satellite dishes, whatever, right? Then we talked about polynomials. Now, I did not talk too much about polynomial functions and where they are in the real world, but things that do this, you know, think about just like stock market type stuff, you know, things that oscillate, you know, they go up, but then they come back down, and, you know, maybe there's points where they're, you know, they cross the x-axis or touch, or, you know, so polynomials can function, can model a lot of things in the real world also. But where would these crazy-ass rational functions come into play? So let me give you an example of a rational function in the real world. Okay, let's say this is time, and let's say it's measured in years. And let's just say that this is the probability that a human is alive. Okay, so let me try and explain this. Let's say that a human is born, all right, and we'll say that at the point where the doctor is like, shit, here we go, that's when we start the clock, okay? So we have a living baby. So at time equals 0 years, the probability is 100%, because the baby was alive to start, okay? Now, I understand kids have problems and things like that, and children are more susceptible to different things, but when you look at the grand scheme of the human population, as time goes on, the probability that you're still alive is going to drop, isn't it? So the probability you're going to make it to your 20s, pretty good, right? What do you say? 50%? More? Most people make it to their 20s? Well, it depends on if you're in the United States or right, what country you're in. But let's just say human beings in general. 20 nowadays, pretty good, right? Let's say 80, all right. Okay, how about to 50 years old? As good, not as good as 20, right? It's going to drop. And then how about 80? Well, now you start talking, are you talking about men or women, right? Let's just say humans in general. And now we're starting to get lower odds, right, that you're going to live that long? I better extend my timeline. How about 100? What are the odds a human will live to 100? Not good, but they're there, right? I mean, there's some probability. I mean, I think I saw it on, I think the other day I read something about the oldest person died the other day or something like that. So now there's the next oldest person who's in line, right? So, you know, pretty low probability. How about this? 200.
It's not too. It's possible. But
Is it possible? Has it ever happened? Not that we know of, right? Is it possible, though? It is possible, right? Or does someone want to argue that it's not possible? Could you live to be 200? Okay, how about this? 2,000. Is that possible? Not possible? Not at all?
I don't know.
We don't know.
Think about
The future
numbers.
can change.
What is 0? What does 0 mean?
Not possible.
0 would mean not possible, right? Now look, no one has ever lived 2,000 years. And no one probably will ever live 2,000 years. However, there is a probability. Now, it would be like this. Probability of living to 2,000 years old might be the same as me winning the lotto, walking outside, getting hit by lightning, going back to play the lotto the next day and winning again, and then walking outside, getting hit by lightning, surviving, and then going back and playing the lotto and getting hit by lightning again, all 1,000 days in a row that happens. Now, could that happen? Could I play lotto 1,000 days in a row, win, and get struck by lightning every day on my way out? You can't say no. You cannot say no. It could happen, right? The odds are infinitesimally small. I mean, this is where math starts to get weird because we're talking about infinitesimals here. It is possible. So what's happening here is we have a rational function. We have a horizontal asymptote. Oh man, that's terrible. We have a horizontal asymptote. What I'm trying to say by drawing this dotted line that's pulling my function is that my function is getting closer and closer to this value without actually ever getting there. So it's approaching 0 without getting to it. Another example would be, how about these light bulbs? You put a brand new light bulb in. What's the probability you think that first flick of the switch it's going to work? You just bought the light bulb at the store. Pretty good, right? Okay, you've been using it, a month later. What's the probability it's going to be working still? Pretty good. How many months later? Now, can you say that 1,000 years from now, assuming there's still electricity and all that stuff, that you flip the switch, can you say it's no way that bulb would work? So it could. So rational function, the horizontal asymptote, is a very good descriptive of this sort of thing in nature that happens, where we approach something asymptotically. That's what it means to approach something asymptotically. We're approaching it without getting there, getting closer and closer without actually achieving the value. And you can actually have it go the other way also. Let's say that this is 100%, and this is money. Good example here. I'm trying to think of something that costs money. What's that? I thought someone was volunteering an answer. Okay, here we go. We all know that the ocean has salt in it, right? Can you remove salt from water? Yes? So if I went out to the ocean right now and pulled out a gallon of water, I could go put it through a process and get the salt out of it, right? I could pull 1,000,000 gallons out and do it also, right? That'd be very expensive. What would be the cost? How much money would it take to get this % of salt out of the ocean? So if I don't want to pull, like this is all the salt in the ocean. If I don't want to get any salt out, it's not going to cost me a penny, right? There it is, there's the salt. But if I want to start removing salt, right, it's going to start costing me money. Yes? Now, what happens is that we can start removing salt, start removing salt. But what happens is that it just gets astronomically expensive. We keep spending more and more, but there's a point where we just cannot get all the salt out of the ocean because the salt's coming from the rocks and the minerals in the earth, and so it's, as we're pulling it out, it's coming back in. It just becomes impossible to ever reach 100% desalinization of the ocean water. Does that kind of make sense?
Yeah.
But again, we have a horizontal asymptote. Has anyone ever seen that movie, Fight Club? Anyone like that movie? No. Don't know what I'm talking about? Yeah, we can't talk about that right now. The guy's an insurance adjuster. One of my favorite quotes all time movies is his quote where he says, on a long enough timeline, the survival rate for everything drops to 0. So that's the picture I just drew for you. Here's time. Here's survival rate, the probability that someone's going to be alive. Right? On a long enough timeline, if your timeline's long enough, the probability, the survival rate for everything drops to 0. It doesn't ever get to 0, but it drops to 0. No matter who you are, what you're doing, we're all dying eventually, right? Okay, so that's where you can, there's all sorts of different applications for rational functions. All we want to be able to do is graph them in here. So let's take our last example. me try and keep these relatively calm and peaceful. How about this? Let's sketch 2x squared minus 18 over x squared minus 3, I don't know, I can't use 3, sorry, minus x. There. Okay, let's try and sketch this. So first thing, let's try our x-intercepts. I still haven't given you a formal process of steps. All I've done so far is said, let's find x-intercepts, verticals, y-intercepts, and horizontals. And I still want you to see that we may need a little more for our steps to do these. How do I find x-intercepts for a rational function? Set the numerator to 0. So I take 2x squared minus 18, I set it to 0. How would you solve that equation? You could add 18 both sides, then divide by 2, and then take a square root. Or couldn't you factor a 2 out of the left side and then see that as being a difference of squares on the left? Either way, you're going to get the same 2 answers. But I wanted you to see it this way because what I need to do is I need to set this factor to 0, this factor to 0. What about 2? What do I do with that 2? Chunk it. Get rid of it. Divide both sides by 2. Don't you still have 0? Okay. So if you ever have a number by itself without an x next to it, you just get rid of it. You don't have to consider it as part of your solutions. One of the mistakes I see when people do this is they'll say, okay, -3 is an x-intercept. Then they'll say 3 is an x-intercept, which is correct. But then they'll say 2 is an x-intercept also, but that's not true. So just be careful there. All right, so what are these again? X-intercepts. I'm going to draw these are dots on my graph. Okay, next thing, vertical asymptotes. To do that, denominator equals 0. How do you solve that?
0.
Is that the only one? Factor the left side. GCF. X comes out, you're left with x minus 1, right? Now set each of those factors to 0. Set that to 0, set that to 0. What do you get? Set that to 0, you get 0, don't you? Set that to 0, you get 1. So we have how many vertical asymptotes? 2. So you remember those dotted vertical lines we drew? We're going to have 2 of them. Next, y-intercept, right? Y-intercept. Look at it this way. Look, we're going to have Thursday off, okay? So y'all just hang in there. Y-intercept. You do f of 0. What's wrong with that? Try and plug 0 in. You get 0 on the bottom. It's undefined, right? So there is no y-intercept. Well, that kind of makes sense because look at where one of our verticals is. X equals 0 means the y-axis, doesn't it? Okay, so I'm just going to put here undefined. And then finally, the horizontal asymptotes. Let's see if you're getting your head around how this works. What are we looking at here? The horizontals. Okay, you look first at the degrees, right? The degrees are both 2's. Since they're equal, we now resort to looking at the leading coefficients. What's the leading coefficient of the top? 2. And I divide that by the leading coefficient of the bottom, which is 1. That only happens when these are the same, okay? I've not given you an example when they're not the same. So my horizontal asymptote will be y equals 2. And now, time to draw. So let me see if I have enough information to draw this. All right, where was my x-intercept, or did I have more than one? I had 2 of them, right? 3 and -3? Okay, so I go out 1, 2, 3, -1, 2, 3. And what do I do there? Points, right? Points on the x-axis. What's next? The vertical asymptotes. Where were my vertical asymptotes? 0 and 1. So x equals 0 means the y-axis, right? How do I draw a dotted line on top of my solid line? Well, this is the way that we do it. We can do it. You can draw little like diagonal dashes to kind of help you see that your vertical is going over your y-axis. So you're not allowed to cross that, right? Where else do you have one? At 1. Now 1's right here. So I'll just draw that one dotted. Like this. What other information do I have? No y-intercept, right? How about horizontal asymptote? At 2. So on my y-axis, I'm going to go up 2. And what am I going to draw? Where am I going to draw it? Dash at the ends only. So I'm going to come over here to this end. I'm going to start dashing it over here. Come over this way. I'm going to start dashing it over here like this. Now the question becomes, is that enough to draw the whole graph? So let's start. And the only place to start is just pick a point. Okay? Pick, how about this point here? As I draw it to the left, what has to happen? It has to go up to that dotted line, doesn't it? That magnet. Now, as I draw it to the right, what has to happen? This is the tricky part. Can you tell me what has to happen? Okay, you can't cross, you mean can't cross this? That's right. This is going to force me up or down, right? Do I know which way? Down? Because if I go down, I go like that. That's okay, right? But why not bounce off and go up? Can't cross what? Can't go like, I can't go like that? No, I'm gonna bounce off here and come back up like that. See, if I bounce and come back up, I'm not crossing in the x-axis again, right? I'm not violating any rule here, am I? I mean, it looks like I could go down without any problems, or I could have bounced off and gone back up, couldn't I? Yes? It makes sense that that would happen. Could happen. Now, it is going to go down, not because it looks like it, but, you know, that's what's going to happen. Now, here's how we're going to be able to, here's how we will tell. When we get to a situation like this, where we cannot determine one way or the other, what's the easiest way to figure out what really is happening there? Plug a test point in, right? Why don't we just try a value of x? Like, this was 0, right? How about this x value right here? What's the x value right there? -1? Why don't we just plug -1 into the function real fast? We call these test points. Let's plug -1 in and see what we get. So plug -1 into your function, you get 2 times -1 squared minus 18 over what was the bottom? I forgot. X squared minus x? X squared minus x. If I plug -1 in there, what do I get? So -1 squared is 1 times 2 minus 8. So -16 on top. On the bottom, -1 squared is 1. Negative is plus. So we get a positive on the bottom, right? So we have a negative on top and positive on the bottom, which means it's negative. And I don't really even care how negative it is. I just know now it's down here somewhere, right? And so I know it's going to go down forever. So whenever we're confused, whenever we're lost and we don't know which way it goes, you can always do a test point. Now, when I get to this vertical, I have to pick my pencil up and move to the other side. Now, what's happening between 0 and 1? You're stuck between two barriers, right? So yeah, it's going to look maybe parabolic. Like imagine we've got to draw something in here. Okay, we can't have this empty space. We've got to be able to do something. So why don't we pick a test point in here and see if it's up or below? So what's a test point in there? 0.5 or 1/2, and you're going to plug that into the original function again. So 2 times 1/2 squared minus 18 over 1/2 squared minus 1/2. Does everyone understand what I'm doing here? Plugging in? Yes.
Why are we drawing another line? We already drew that one.
Okay, because the vertical barrier makes me have to stop and move on to the next part of the graph. The next part of the graph that I'm looking at is between here and here. I'm trying to see what does my function look like inside of these, between these two lines, vertical lines. Are you saying like we already drew this? Well, we still have all the rest of the graph to draw. Remember, our graph is going to have, we're going to have a picture everywhere except these two dotted lines. Everywhere other than those two dotted lines, we should have graph. So we're going to have graph over here, we're going to have graph in the middle, and we have graph over here. So it doesn't stop this. Okay. All right, yeah. We have a long task ahead of us here. So what do we have there? Does that turn out to be positive or negative when you do all that? Has anyone done it? 1/4 and a half. Negative on top, negative on bottom. So negative divided by negative, you'll get a positive number when you do that. I'm not going to go through it because everyone has assumed that you could evaluate a function. So you could plug numbers in and get an answer. All that matters to me is it's positive. So that means I don't even care where it is, it's just up here somewhere, okay? So I have a point up there. What does that tell me? Well, as I try and draw this thing out to the left, I run into a barrier, right? That barrier is going to force me which way? Well, either up or down, right? But now you can tell me which way it has to be. It has to be up, because if I come down, what happens? I cross the x-axis. So it has to go up when I go to the right, right? And then when I go to the left, it has to go up. When I go to the right, what has to happen? Same thing, it has to go up also because if it comes down, it crosses the x-axis. So I've got almost like this little, it's not quite a parabola, but it looks kind of like a parabola. Parabolas look like U's, but they go out forever. This U is trapped between two walls. We're almost done. I'm going to jump over the next vertical because that vertical forces me to now look into the next region, which is over here. I do have a point here. Can you tell me anything about where I have to go from here? Just do that. But I mean, anything? Just whatever I want? What has to happen? I know for sure it has to do that, right? That's what that does, right? Pulls me up towards it. To the left, though, what? Down? It looks that way, right? But it could also have bounced and come back up. So this is another one of those problems where we have to test another point. So remember when I said that, we have these four things. We have the x-intercept, we have the vertical asymptote, we have the horizontal asymptote, we have the y-intercept, but that's not enough. I haven't given you the steps yet, because the steps need to include this idea of test points. So that's why I've kind of waited. So what's a good test point right here? Well, that's 1, that's 2, right? Let's plug 2 in. Plug 2 into the function. 2 times 2 squared minus 18 over 2 squared minus 2. What is it? Negative? So it's negative. Again, you can figure out exactly what it is, but I just care that it's negative. Does everyone see, though, that if it had turned out positive, then that means I would have bounced off and come up like this? That's what it would have meant if it was positive, but it's negative, so it does what it kind of looks like it does. There it is. Y'all remember me telling you about that website, Wolfram Alpha? Yeah, they have an app. So if I go to Wolfram Alpha, now if you're going to type this function into Wolfram Alpha, you have to separate the numerator and denominator with parentheses. So I do parentheses, it was 2x squared minus 18 divided by the denominator in parentheses, which was x squared minus x, right? There it is right there. You don't see that right here? So our graph, sorry, it's kind of hard to see it, but this is it right here. It goes down and down, and then here's that little U. You see it? Unfortunately, Wolfram Alpha used to be able to zoom in and oh wait, I think I know how to zoom in. I think I can force it to zoom from -5 to 5. Well, that kind of works. It shows this part of it, and it shows this part of it, and then what the hell is this? What the hell is that? That right there is the vertical asymptote. See, even Wolfram Alpha, which is a very powerful computing machine, doesn't know how to deal with the vertical asymptote. You know how I said when we plug in numbers, it's getting huge or whatever? The computer's going, and freaks out and just says, I'm just going to draw a vertical line. That's basically what it does. It like concedes to infinity and just draws a vertical line. So you can see there's actually one vertical line that's being drawn here, and there's another one on top of the y-axis that's harder to see. But it gives us some, feeling of accomplishment that we're getting the same graph. Of course, this took us half an hour, and that took me about 15 seconds, right? But that's his life.
Well, you know how many lines are in
How many lines or how many test points? Like these vertical ones?
drawing specialists?
Well, you can approach it that way if you want. Look, would you consider this 3 different sections? Okay. How many vertical asymptotes did we have? 2, right? If we take our number line and we cut it with 2 verticals, it creates 3 regions, doesn't it? And we had 3 sections of graph. We had something to the left, in the middle, and the side. So yes, that's one way. If you want to approach it that way, you can. If we have 1 vertical asymptote, we should have 2 pieces. If we have none, we should have 1 picture. If we have 5, we should have 6 sections. Make sense? Okay. So what I will do is give you an assignment for you to work on for homework. I'm going to cut you loose early 4th of July. However, I would like to speak to anybody who is on their phone texting today. I want to talk to you. Okay? Now, if you walk out of here like you weren't texting, then you'll get penalized. Because I know who you are that have been texting. I want to talk to all of you. Okay? Understand? So I'm going to give the assignment. I'm going to let everyone go. Everyone who's texting on their phone, y'all hang out so we can talk. All right?
Do you have time to go over the quiz?
I can, yeah, afterward. What do you mean? The problem
So
that we
when
did
you
earlier?
look at my quiz,
Yeah, we can talk.
what I
Yes.
did wrong.
Absolutely. Okay, so what I would like for you to do is on page 357, starting on, let's see, we're going to do number 49. This is just the first day of homework, so I'm not going to make it too extreme. I'd like for you to just do those two problems. Now, the book says use the guidelines for graphing rational functions. All I want you to do is go through what we did today on those two problems, all right? Go through the steps. And then when we come back, what's our schedule for next? We said we're pushing everything back, right? So next time we meet, we are going to do, on Tuesday the 8th, we are going to do more graphing. Okay, more of this graphing. We are going to review for the test, which is really just going to be, the test only covers quadratics, polynomials, and rational functions. And then that Thursday, so next Thursday, we are having our second exam.
So this second exam is going to have this combined?
It's going to have, next Thursday, a week from this Thursday, right? Next Thursday. We are going to have a test that requires you to graph a quadratic function, polynomial functions, and rational functions. Yes. So it's important for you to be here on Tuesday because I'm going to cover more of these. But you'll pretty much, by the next time we meet after that, have to be able to graph. Yes. The attendance? Yes. Anyone else need attendance? No?